Hello everybody, what is up? Another week of CS202, moving along and talking more about pointers. I hope you all had a good weekend. So, last time we left off talking about dynamically allocated variables, and I was just showing you how new and delete work. Oof, I am seeing some lag on the video stream. Let's wait a second and see. Can you guys hear me? Can you guys see me? I'm getting really low bit rate. Okay, it's recovering now. Okay, it's up now again, so I guess I shall keep going then. It's like hovering all over the place. So hopefully you guys are there, but we'll see. Someone say something on chat. Just make sure that we're back up now. I see it green again. So, okay. Well, anyways, for those on YouTube, I guess we had a bit of... I can monitor when the bitrate is dying, and there for a second, it was dying. So, anyways, today we're going to keep talking about dynamic memory allocation. And so, last time we stopped by introducing new and delete, the two operators that are new here. And so I showed you a little bit of code on how to use them, but we just kind of stopped just slightly introducing them. And so we're just going to pick up from there. It's clear, Doc. I hope there's no massive delay. See how long it took for your message to pop up. And then, hopefully it's okay. Otherwise I can restart the stream if it's really big delay. It's never good when I have those big lag spikes right at the beginning of the stream because it just delays everything. I can actually, there's a way to do a stream preview, but I don't want to strain the internet more. But anyways, so continuing on, I showed you examples of basic one-dimensional array dynamically allocated. And so what I was telling you with the new and delete is that they return an address of the dynamically allocated memory. And so you got to store that address somewhere, otherwise you can't access it ever again. And so let's just jump right into coding today so that we can show you how to do these things. Okay? Okay, and so if we create a pointer, well, first of all, as I showed you last time, I'll show you again. You can use a new operator without anything. You can say new int. What does this do? Well, I'm putting it inside of a CL statement so that we can see what it does. But all it's going to do is going to allocate memory. It's going to say, hey, operating system, please give me one integer slot. Or actually better said, one slot of memory the size that an integer needs. That's probably a better way of saying it, okay? And so if I run this, I see that, well, let me save it and then run it again. I see that all I'm getting back is an address. That's actually the address of the slot of memory that you were allocated by the operating system. That will change every time you run because you're basically asking the operating system like, hey, I need a spot of memory big enough to hold an integer. And the operating system just picks pretty much randomly from its available memory. Not intentionally randomly, but it's just more like what's available, just kind of like put your finger at a paper and that's kind of what it gets, okay, for an oversimplification. And that is why every time you run it, we see that there's a variation in the addresses. Pretty big too, because remember, these are hex values. So this is where pointers come into play. That's why we've been talking about pointers for quite a while now, because what are pointers for? What are they useful for? They're useful for storing addresses, right? And what we're getting back when we call the new operator is an address. So all we need to do is store that address in a pointer so that we can use that variable in the future. And so how do we do that? Well, let me show you. Make an int pointer, we'll just call it PTR. And in that pointer, we are going to store the address that we're getting from the operator new. What this is doing is, this is storing the address that we're getting back from the operating system. So if I do this again, I'm going to get just more addresses again. except this time I'm getting the address that's already stored in PTR. That's good because now I don't lose that address. Because remember, if I do something like this in C++, like if I say 2 plus 2, like that, this will compile just fine. Like it won't give me any errors. Unless maybe I do like wall or something. It's just not going to give me any errors, right? What's happening is you're adding 2 and 2 together, you're getting 4, and the answer is just kind of being thrown into the void. You can think of it like falling here, like woo, just falls down into the void. Same thing with the new operator. So what do we do normally in this case? Well, we store this in some sort of variable, right? Same thing with dynamic allocation. We store it in a pointer variable. Could we store it in a regular variable? Well, I think it will compile, but it would not make much sense to store it in a regular integer because it's an address. It's not just an integer or something like that. But here, let's just try it for the sake of it. This might give me a number that will be weird. And valid conversion, so it doesn't even let me do it. I can force it to do it by using this flag, which you really shouldn't use unless you know any better. It turns as an error tone of warning. And then when I try to see out it, well, let me actually see out it. I'm going to see probably some weird number that won't really make sense because it's going to be in decimal instead of being in hexadecimal. But basically, I suppose this could be a quick and dirty way of converting hexadec. If instead of storing a new integer, I store like PTR, which is an address. Semicolon. So the question is this the same as this in decimal versus hex? Let's just do a quick check. Hexadec. And see, it might not be because of the fact that one is basically two's complement and the other one is not. Basically one is signed. But no, it turned out to actually indeed be okay. So yeah, so this is actually a pretty neat way, I suppose, of converting a hexadecimal value into a decimal value. That actually is indeed correct. So yeah, cool. I wouldn't recommend you do that because it's kind of bad, but you know, weird. But I guess it could work. And if you really wanted to see what the address was in decimal. So anyways, going back to this. So we have stored in PTR the address, right? And so remember that we have the dereference operator, and that's what we're going to be using to dereference that address. And so if we do this, we're just going to get garbage probably. I mean, 0 if we're lucky. Yeah, 0 if we're lucky. So there you go. But technically, it's just whatever was left over from the previous program that used that memory slot. It doesn't get initialized to 0, right? It just happens sometimes here that it does, but you can't trust it because it may not always be the case. You might get like a negative number there and your whole program breaks, right? So if you want to initialize it to something, or say you actually just want to assign something to it, use the reference operator, and there you go. Now you have dynamic memory. This memory is allocated only when the code sees this line. Now this is of course kind of like the first line of the code, but suppose there was like a billion lines of code right there in line 5, okay? That means that this memory that PTR is going to hold does not get made until you get to this line where it says new. And that's good because you don't need it before that. So it's a waste to reserve it ahead of time, right? So that's one of the big advantages of dynamic memory allocation. Now, as I said on the other side, with delete is going to return that memory when you're done. When you always want to return the memory to the operating system when you finish using it. If you don't, it will claim it when the program ends, so that's, I guess, a good thing. But suppose that you're using a big chunk of memory to process some data, and then you stop using that because you don't need to process that, or you process the data anymore, you save it to a file, you're done, but your program still runs. You're still holding off to that big chunk of memory. It would be good to return it at that point so that other programs that are running concurrently with you, so like other programs running at the same time, can go ahead and actually take advantage of that memory, especially if it's a limited resource. Suppose that you're processing like some serious data and you are using like 50% of the RAM capabilities on this one big file. That's okay. That's what RAM is for. I mean, you paid a lot of money for your RAM. You might as well take advantage of it. However, you know, you're only using it for that piece of the code. And when you're done, you know, why hold on to it? Give it back to other programs so that you know your other programs don't get slowed down if they also need a lot of memory, right? And so the idea of give and take is you know, it's very, very important. And so the way that you return that memory is you call delete and then you pass the address that you're trying to get back. So in this case, that address is being held in PTR, so I go ahead and call delete on PTR like that. Okay? And so you don't see anything happen here, but you have returned the address. And so this brings us into the next topic. So starting from this assignment, which I believe is assignment 4, but whatever it is, you have to run a special piece of software called Valgrind to check your programs for memory leaks. So what's a memory leak? Okay, so let's go back to the iPad and talk about that. So that's kind of basically where we left off last time. I was going to introduce memory leaks, okay? But I wanted to kind of refresh you from the long weekend. So let me visually again. I did this at some point. Actually, I might be able to copy paste it, but now I'll just redraw it again. So let me again visualize for you the memory, right? So the memory, you know, yes, we have stack and heap and whatnot, but for now, let's just kind of put it like one big chunk of memory, okay? And so this memory is in hexadecimal, the addressing system. But it doesn't really matter for the purposes of the example, okay? But I'll just put a couple of addresses here. Okay, so this is our memory right now. And so, remember, we are dynamically allocating memory, which means we are requesting memory from the operating system, okay? So, I go ahead and I write the following code. Int PTR, like I did before, gets new integer. Okay, so what this is doing again is asking, hey Linux, or hey Windows, or hey iOS or Mac OS, can I please have one chunk of memory big enough to hold an integer, which is probably going to be 4 bytes. The operating system goes ahead and says, sure, no problem. I'm going to go ahead and give you this piece of memory right here, address 300, okay? So now PTR, which has to be held somewhere as well, we'll say it's held in address 100, so this is PTR now. That is going to get stored the address that you got from new, which is that, okay? So the operating system says, takes address 300 in hex and sends it over to PTR to store. And so PTR itself is a variable. So this is one of the things that a lot of people always mess up. PTR is actually a variable on the stack. It's not even on the heap. It's a variable that you have a compile time that you define, right? And you know it's a variable because there's no new in front of it. It's just good old variables. This right here. This is just a good old variable. And that variable also has to be stored somewhere in memory, right? And so it's the same thing if I said something like int x gets 5, okay? Let's say x gets stored in address 200, okay? X lives somewhere, okay? And so does PTR. However, PTR can hold addresses instead of just regular integers, right? So PTR lives at address 100, but the contents of it is 300, which happen to stand for address 300, okay? So the only dynamically allocated memory in this program so far is address 300, okay? So there's technically, in this case, if we said that the pointer was also 4 bytes, this program is currently using 12 bytes of memory, okay? 12 bytes of memory. It's using 4 bytes for this, 4 bytes for this, and 4 bytes for that, okay? So 4 bytes times 3, 12 bytes, okay? Of those, 8 are in the stack, and 4 are in the heap. And in other words, 8 are kind of defined at compile time, and they always will exist for the entire duration of the program. And then 4 bytes, which is the new int part, is going to only exist after this line of code, okay? So, cool. All right. So you go ahead and you do some math, you know, you take PTR, you stored the answer of 2 times x, okay? That's a good one. So that's going to technically store what? It's going to store 10. So where's 10 going to be stored? It's not going to store in address 100. because we are dereferencing PTR, which means we're storing it in the dynamically allocated variable down here. So, oh, not 100, sorry, 10, okay? And so that's where you're storing the 10. Cool. Now watch very carefully what I'm about to do here. You're so excited that you're making all this dynamically allocated variables that you're like, let's go ahead and make another one. So you say PTR gets new integer, okay? You do that, and so the operating system is basically saying, hey, you need another integer variable? Sure. Let me go ahead and pick an address that I have available. So let's say it just picks address 0x150. So that's going to be the next address that it picks. Okay, that's also dynamically allocated. So now we have 16 bytes in our program, 8 on the stack and 8 on the heap. Okay. Here's the thing though. We got to update PTR because we're saying PTR new int, right? So that means that PTR, which lives at address 100, the contents of that are no longer going to be 0x300. It's going to be 0x150, right? Because that's the one that we got from the operating system. And so now, you know, we can store it into PTR, I don't know, another number for some reason, 5. And so what is that going to do? That's going to store 5 there. How does that work? We dereference PTR, which means we go to address that is contained in PTR, which is address 150. So we go to that address, address 150, and we store 5 there. Okay, here's a problem. Suppose now we want to deallocate memory because we finished using these variables. We still got other code to do, but at this point in time, we want to return the memory. So we go ahead and say, okay, cool. Let's just go ahead and call delete on PTR. What this does is it tells the operating system, hey, I no longer need this address. Now, what address is currently in PTR? PTR has address 150, right? And so what happens here is it goes into address 150, and let's just say it marks it as unallocated. So I suppose I'll pick a different color for that, okay? So I kind of graze it out like that, okay? The content is still there. The 5 is actually physically still stored in memory, okay? But you have returned that memory allocation to the operating system. What that means is that you no longer, quote unquote, own that address, okay? Furthermore, before we talk about what that kind of can cause, let's talk about what we already have caused, which is, here's the thing. When we did delete PTR, we've only deallocated this address. But what about this one? What about address 300 that had the 10 in it? That's still allocated to us, but we didn't delete it. And why is that? Because we called delete PTR. Well, it turns out that your delete PTR is calling delete on address 150, which is what PTR holds. The problem is that up here, we overrode what was stored in PTR, right? We overwrote the 300 with 150. And so we've lost, basically, we've forgotten where the original PTR value was, which was 300. This is what is known as a memory leak. And technically speaking, the actual memory leak happened when we did this line of code, because that's actually when we forgot what was in PTR because we overwrote it, okay? So to give you a more layman's term example of what we did, this is the example that I like to give. I don't know, the first time I thought about it, I thought it, and people liked it, and now it's just burned into my memory. So you live in a world where everybody has the right to free housing, okay? And so in this world, to reserve basically an apartment, all you gotta do is go to the main office of the apartment complex and be like, hey, I'd like to get a place here. And then they go ahead, they look in their list of available apartments, and they give you the keys. They themselves have another copy of the keys, just, to be safe, but they give you the keys. There's only 2 copies of the keys. You get one of them, okay? And so you go and you live in this apartment, okay? This is like you allocating memory, because now this apartment is yours. Now, technically speaking, it's not really yours, right? Because it's the community's apartment, right? But you are currently sort of leasing it, right? And so until you actually return it, because you got to move out or something, it's yours and nobody's going to mess with you. The apartment owner, the apartment complex is not going to go and kick you out. You're just, as long as you're still alive, okay? If you happen to die, they have other keys so they can clean out and still loan it out, okay? But that's kind of the basics, okay? Here's the thing. You go ahead and say, well, I'm starting up a business, so you know, I want more space, and so you want to ask for another room in the apartment complex. So you go to the leasing office and you get the second one, okay? And so now you have 2 rooms. But here's the thing: when you take the second one, you know, you take it home with you, and then you only have one place to hang keys, okay? And so you take, and you can take up that as your variable PTR. And so you take the keys from the second apartment, and you got to remove the other ones out to put the other ones in, okay? And then you just kind of leave them on the table there. But here's the catch: if any of you have seen like the movie Memento, some people have, I don't know if I said some people in real life, but at least in the movie, they have a condition where you have amnesia, where like every time you go to sleep, you forget everything, okay? So the only way that you can remember where you live, it's because you have the keys there hanging on your little door key holder thing, okay? And so you go to sleep, and the next morning you wake up and you of course don't remember anything. So you look at your notes and whatnot, and then you see in your notes that your keys to the apartment are in the thing up there. You go look up there, but you only have the keys to the second apartment. You don't have the keys for the first apartment, right? And so you yourself can no longer even go into the other apartment, assuming you're in the second apartment at this time. But you can't even go back to the apartment because A, you might have written somewhere down that you had a second apartment, but you've lost the keys because you didn't put them there, or because you overwrote the only location that you had them. And so now, even though the apartment complex has it assigned to you, you know, you have no idea where that apartment is. Or better yet, you just don't even remember that you had the apartment because amnesia, right? So that's kind of what's happening here. There's 2 problems with that. One of them is you don't remember where it is, you can't even use it. So that sucks, right? Like you have an apartment, it's loaned out to you, it's reserved for you, nobody else can use it, you can't even use it. The other bad side of it is that because you don't have any memory or don't even know where the apartment is, which don't know where the keys are, other than you not being able to use it, you can't return it either. So even if you wanted to be the Good Samaritan and return it because you're like, oh shoot, I forgot, you know, it's like saying, could you go to the operating system and be like, I forgot which apartment I have, but I have on record that I might have an apartment at some point. That doesn't really work out. They don't keep track of that because of privacy or whatever. They only know that you have some apartments, but they can't look it up unless you die. That's the only time where they can look up in this like secret book for your own privacy protection. Okay? And so because of that, you can't return it and you can't use it. That's very, very bad. So what ends up happening, if you need more memory, well then I guess you're gonna get a third apartment, okay? So we'll come back to this example when we talk about the other side of the coin, but going back into programming, that's essentially what a memory leak is. You lost access to a location that was allocated to you, and because of that, you cannot use it, and you can't even return it, which means it's gonna stay with you until your program ends, and then it gets returned automatically. That's bad because typically memory leaks are not a one-off time. They typically are reoccurring in a loop or something like that, and they build up over time. And what that entails is if you have a piece of code that is in a loop, and every once in a while it allocates more memory just because of the way that it's written. It's not intentional, but it just happens to be like that. Over time, your memory allocation usage is going to rise. Eventually, long enough the time, you're going to get to a situation where literally all apartments are going to be in your name. And then you are going to try to request one more apartment, and then they're going to be like, I'm sorry, we're completely out. And then your program is going to basically crash because you basically require to have the apartment. You require to have a new allocation. You can't just like stop. You can do try and catch and sort of avoid it, but other than that, If you call new operator, you expect to get a variable back, an address. And if you don't, that's an error and your program terminates. And then, hey, all the memory is returned at that point, which is nice. But yeah, so very, 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 very bad thing to do, to slowly hog memory. However, sometimes in this class, I expect your code to be without memory leaks. But in the real world, I am going to warn you that sometimes it's so expensive and difficult to fix all the memory leaks that there's a certain degree of acceptable memory leaks in the program. What that entails is if any of you play video games, you've given enough time that you leave a video game running, it will slowly grow up in its memory usage until basically your computer slows down to a grinding halt, or better yet, the whole program just crashes, right? I'm sure you have run into those situations before. Or even like Google Chrome is kind of known for having a few memory leaks, and most browsers in general. Basically, most programs that that are relatively sizable, they're not like baby programs, will have a certain degree of memory leaks that is just to be expected, and you just have to deal with it. The important thing is to kind of control that from getting out of hand. That's when it causes a problem, when it causes an issue to a user. Other scenarios, like if the system is like mission critical, like let's say that this is a program that handles like a respirator, okay? That you don't want to have a memory leak. That code has to be super beautifully checked, because if it crashes, now you're playing with somebody's life. Or like imagine an autopilot in a plane or something like that. In those kind of situations, you have to be extra careful about memory leaks and things like that. But for most general use things, like for example, running a video game, it's like whatever, how long before the program actually crashes the computer or something. You have to run the game for maybe like 2 or 3 days. Fine, no one's gonna run it that long, so whatever. If they do, then they probably want to take a break anyways. And so that's kind of what happens. Okay? And so, how do we fix memory leaks? Well, easier said than done, but what you want to do is you want to keep track of dynamically allocated variables, which are stored in pointers, and make sure that you don't overwrite the pointer before you deallocate it. And if you have a situation like this where you're reusing a pointer, you may have to consider rewriting the code in a different way so that you don't lose access to the variable. In this very, very specific instance, well, I could just go ahead and write delete here, PTR, before overwriting it. And that will go ahead and fix memory leak in this specific case, okay? However, easier said than done, like I said, with real programs. So, now we can go back to the computer for a minute, and I can show you a tool that I kind of introduced last time that can help you see whether you have a memory leak or not, okay? So first of all, let me go ahead and I'll leave the code like that. We just go ahead and run it. So the tool is called Valgrind, spelled out like that. And the way you run the tool is you type in Valgrind, and then you put in the name of your executable. So like /a.out. When you run it, it says memcheck, a memory error detector. Because some copyright information, and it talks about the heap. See, heaps are a real thing. And it will tell you how many allocations you have, how many frees you have, and how many bytes you had allocated when the program ended. Now, this should normally be 0. In this specific case, if you're running an old version of Valgrind like I am, there's a I don't know if it's necessarily a bug, but the reason it says that I have some memory still reachable is because of the built-in libraries in C++ for IOStream, like C in and C out stuff. So it actually says that I have 72,000. It always says the exact same amount, like 72,704 bytes. That doesn't mean your program has a leak in it. That's okay. Like I said, if you run this in Sally or something with a more modern Valgrind, it actually they fixed this because people kept complaining. So if you Google this, you get basically the same thing I said. So anyways, the important thing that we want to see is that we see here that the leak summary, that refers to memory leaks, has definitely lost 0, indirectly lost 0, and possibly lost 0 in 0 blocks. Okay, and down here also the error summary is 0 from 0 context. This is what I expect all of your programs to be before you turn them in. From now on, as policy happens to be, if you turn in a program with a memory leak and the PDFs doesn't specifically allow for that memory leak or a certain degree of memory leaks, which I don't think any of them do, then you will lose a lot of points in your assignment. Refer to the syllabus for that, for how much you lose, but you will get deducted points for having memory leaks because we're trying to instill good practices, you know, at this level, so that you at least try to get rid of memory leaks in the real world. Okay. So let me show you what this looks like with a memory leak. Let's get rid of the delete. So now I've allocated an integer, but I don't deallocate it. So if I recompile this and run it again on Valgrind, I will see that it says definitely lost 4 bytes in one block. The number of blocks is typically the number of allocations you did. So like an integer I said is 4 bytes. So this is referring to 4 bytes in one block because it's just one integer. If I did like a double instead of an integer, then I would probably see 8 bytes in one block. Now, if I did an array, that's when you will typically see a lot of bytes in multiple blocks as well, or a combination of different things. Okay? Also note that Valgrind does show you the output of your program. It's just kind of hidden amongst everything, but this is actually the output of the program. You know, if I scroll up, like you see how I ran it had an address and a number 5, that's pretty much the same thing here. There are also errors. What can I do to make an error come out? Let me see. Oh, probably try to delete something twice would be a good sign. Sometimes, if you try to delete a pointer twice, you know, the first time you return it, but the second time, what does that mean? Well, that's bad. It's undefined behavior, and it typically results in a crash. However, it's not always. So, you know, you might be like, well, let me be extra safe. Let me just delete everything like 50,000 times. No, because that's literally going to cause more problems than solve. As you can see here, that all caused an error. I don't have memory leaks. That's good, but I have errors. And if you look at the errors will actually show up around the line of code where you're doing it. And here, this very clearly says invalid, free, or delete, which means that you called delete on something that you really shouldn't have, such as on something that you already deleted, or worse yet, suppose you try to call delete on a variable that's in the stack, like int x, and I try to delete x like this. Okay? You can only delete dynamically allocated variables, right? Okay, let me the compiler's trying to save me from doing something I will regret. So let me put ampersand x to get the address of x. There we go. So if I do this, actually, will it crash on its own? It seems like it didn't crash. No, it did crash. See, it core dumped. So it does crash. But in Valgrind, if I run it, it didn't necessarily core dumped. I don't see it generating an exception. However, I do get the error saying that this address that I'm trying to delete is on the stack, which is a sign that you're trying to delete something that you shouldn't delete because it's not dynamically allocated, okay? So this, of course, causes some issues because, like, as we learn later about, like, arrays of pointers and things, you might mix and match, like, stuff that's dynamically allocated with stuff that is not. That is a pain because then there's no way for you to check where it's stored before you call delete. You have to keep that sort of management on your own. In fact, there's no way to check whether something you've called delete on has already been deleted or not without doing something like a smart pointer or like doing your own management of that. So, like, if you're asking, how do I know when I call delete PTR, like right now it's obvious. I see that I'm typing delete PTR. But as we learn about like things like linked list and whatnot, where you're using pointers all over the place, you might not know whether you deleted something or not already. There's no way to check it with code. No easy way. No portable way. And so it's all up to you to figure out managed ways of doing it, such as like making it a class and putting a boolean there to know if you called delete on it or not. That's gonna keep track of it, like a little checkbook. So, anyways, that's how Valgrind works, and that is how memory leaks work. Now, let's go back to our example here. So, we have learned our lesson with memory leaks, and so we go ahead and call delete here, and then we also call delete here, right? Okay, I'm gonna talk to you about another issue that we might have here. Suppose that after this line of code, after the second delete, you know, I go ahead and say cout ptr, or worse yet, I say ptr gets 42, like that. Okay? So this is bad. This is really bad, actually. But Not as bad as memory leak, I'd say, but still on the this is really bad category. Here's the thing, and this is why delete is a misleading name again, which I said last time. Delete in C++ means de-allocate, and what it means is you return to the operating system the memory. When you return the operating system the memory, all you're doing is you're literally handing over the reign of that location and saying, hey, I don't need it anymore. You're free to give it to somebody else. However, PTR is a pointer, right? And in our example here, PTR still has address 150, which is the location that we previously had in PTR, right? Or sorry, that was previously allocated dynamically. And so here's the thing. I have that address still. If I have that address, I can still access that address by using my dereference operator. Even though it's no longer owned to me, I can still access it. And the worst part is, more than likely, if I try to see out immediately after I delete, 99.99% of the time, the contents will still be there. So calling delete is not erasing anything. It's merely giving away ownership to that area, back to the operating system. And so why would I do this? Well, I might not be aware that I have already deleted it, or I might have forgotten in general. And so I can still access it, and worse yet, I can still probably modify it and keep using that variable as if it was dynamically allocated to me. However, it doesn't belong to me. Given long enough time, this could cause some serious trouble because you could be writing into memory location that is not yours, or it could even be technically, although there are safeguards in place, but it could technically be given to somebody else. So let's go back to the apartment, story that I was talking about. Suppose that you have an apartment, and then you got the second apartment, but you wanted to return the apartment because you're done. You moved somewhere else, and so you go back and you hand over the keys back to the apartment complex, right? But here's the thing. You still remember where you used to live, right? But you don't go there anymore because it's no longer yours, right? But then one night, you get drunk, I don't know, for some reason, and then you're basically drunk, and you're walking home, and because you're drunk, you forgot where that you moved, and you walk into your old place. And here's the thing, it's unlocked because the operating system, since it didn't give it to anybody, it's just unlocked. It's just like whatever, it's a safe society. You go in there, you sleep there, you wake up the next morning, you're like, oh snap, I shouldn't have done this, and you go. You got lucky that time. Okay, second scenario, guess what? This apartment was in high demand. Turns out that they actually rented out your old apartment to somebody else, right? Fair enough, it was free, it was available. Somebody else might have wanted it, and they took it. You go in there, the people there are like, what the heck? Somebody's breaking in, and then they either shoot you, beat you up, or they attack you, right? Because they think you're like a robber or something. Too bad, I guess. Do you want to be in that situation? I don't want to be in that situation. I don't drink at all, but still. The point is, very, very bad things can happen, right? At that point, you're at the mercy of, it's no longer yours. You never know what's going to happen when you walk in there. Same thing here. Yeah, sure. You might have given back the keys, and they haven't rented out the place to somewhere else, and they haven't given out the variable to another program, so you can still probably play around with it. But that may not always be the case, and you're still playing with fire by using a variable location that is no longer yours. Okay? That has a name in programming, and that is known as a dangling pointer. And there's a solution to this. The solution to this is to forget where it is. So, if you return an apartment, to the complex, but you have like a drinking problem or something, and you're always drinking, and you seem to always go to all places you live, well, suppose that you could use those Men in Black scanners that like clean your brain, you know, for a certain amount of time. You do that on yourself, and now you completely forgot. So even if you're drunk, even if you don't know what you're doing, you will never by accident go back into the old place. That's essentially what you want to do here. After you deallocate some memory by returning it, by calling it delete, the next thing you should do immediately to be safe is forget where that was so you don't access it by accident. How do you do that? Well, if you remember, how do you initialize pointer variables? You initialize them with null or 0, right? Because that's a good thing that we can always check with an if statement to see if it's like unused variable. Do the same thing here. It's like reinitialize them, I suppose. So in this case, you would do something like ptr get null. And by doing that, you basically erased that. So you go in here and you erase that 150, which is that address of where you used to live, and you put a 0. And so now, hopefully anytime you use your pointers, you're still checking if it's not null. And then you will see that it's null, which means that you probably shouldn't be accessing it because you haven't allocated it. Or now the second scenario, that it was yours, but you return it, so you don't want to accidentally go to some place that no longer belongs to you. Okay? So those are the two major issues that you have to deal with when handling pointers: memory leaks and dangling pointers. Okay? Memory leaks you solve by ensuring that you deallocate variables when you finish using them, and make sure you don't overwrite the pointer that contains that address so you can still access them. So basically, don't lose your keys. Dangling pointers you fix very easily, and you should make it a good habit. Anytime you call delete on something, immediately afterwards set it to null. That will avoid problems in general. At least while you kind of get a feel for it, it's a good practice to do. Afterwards, you know, it may not be totally necessary, but technically speaking, until you set it to null, it's considered a dangling pointer, which is risky because you may accidentally access it unintentionally. Hopefully unintentionally. Okay? By the way, some operating systems are more strict again than other ones when it comes to this. But this is kind of like the same scenario if you ever allocated an array in C++, and then the array was like of size 10, and technically those indices are from 0 through 9, right? But suppose you kind of forgot about that, and you made your loop go from 1 to 10. 1 through 9 is okay because that's in the array, but technically spot 10 is outside of the array. Some computers will crash. They'll be like, nope, you're accessing outside the array. This is forbidden land because this is no part of your program. You crash. Other computers are more relaxed about it. They'll actually let you right there because it's like nobody's looking kind of thing, and you kind of get lucky, basically get lucky, and so it won't crash. And you could have your program running all day, and you think it's okay, but then you go test it on like Sally or another computer, and it crashes, and you're like, why? Could be because of this. So even though that's technically not a dangling pointer or a memory leak, but it's still related to that, where you're accessing memory that does not belong to you. Okay, but that's even worse because like the heap is more like relaxed. The stack, would be what we were doing in that scenario, that's bad. But most of the times, you'll learn more about this in 2.19. They usually have like a little buffer area of like screw up area, I call it, around memory that gets allocated in the program to avoid this kind of situation because it's just expected to happen once in a while. So, anyways. That pretty much concludes the memory leaks and dangling pointers and the basic introduction into allocating memory. So now let's go ahead and start practicing allocating multi-dimensional arrays. Let's do. I think we did last time at 1D array, but I'll do one again. But again, what we really want to focus on is multi-dimensional arrays because that's a lot more interesting. Okay, so let us go ahead and just kind of start out clean. I don't really think you need that piece of code to be shared, so I'll just delete it. Plus, we had an example last too. Let's make a 1D array first of all, okay? So let's just call it our R, and then allocate it. You can always do the same, declaration and initialization on the same line or 2 lines. And so you can do something like X there, okay? And then X can be a variable, which for the heck of it, we're gonna make it a pointer, why not? That is going to define the size of the array, and we're going to read that in from the user when the program starts running, like that, okay? And so what this is doing is I'm declaring a variable I'm declaring a pointer variable x, and I'm allocating a integer from the heap using new. That's the first line of code. Then I'm reading it into that variable, which I need to dereference because otherwise I will be trying to overwrite the pointer itself with whatever I'm reading in from the user, which is the size of the array I want to make. Finally, I'm making another pointer variable, and this pointer is not going to hold a single integer. It's going to hold an array of them. And how does that work when it comes to pointer? Like, what does the pointer hold? Does it point to the first part of the array, to the middle, to the end? Turns out that in C++, your arrays are just smashed together, like neatly, like stacked on top of each other. And so all it does is it points to the first element of the array. And basically, it will do what is known as pointer arithmetics, which we'll talk about probably next class. And it'll do that to basically traverse the array. Okay, so int r is going to hold the address of the first element of the dynamically allocated array that we're making here. The size of the dynamically allocated array is going to be x, but technically it's going to be asterisk x because, again, x is just a pointer because we chose that to be the case. Okay, now let me go ahead and just make a little for loop that will initialize my array to some just random data. How big do I want to loop this? X size, of course, and then I++. And how about we just set the array to be I? Yeah, why not? I'll give it some variety. And then finally, I suppose it might be good to print out the array. So basically the same for loop, except this time we're going to see out the array, and maybe we'll just put everything in one line with spaces. And maybe an end line afterwards. Just one single end line. Okay? This course could be written much nicer, but I'm smashing it together so it fits on the screen, right? You don't want to do your for loops like that. So, okay, we run it and it's expecting us to put, so let's start out with maybe 5 for the size of the array. As you can see there, we have an array of size 5. Now, what did we forget in our program? Well, we forgot to de-allocate stuff. We probably got some serious memory leak issues here. All right, let's go ahead and check it out. Let's run Valgrind. Well, it's expecting a number, so I guess let's try 6 this time. We can see that we indeed have an array of 6 integers in there, and we can see that it says we allocated 5 times, we only freed 2 times. We have definitely lost 28 bytes in 2 blocks. Why 2 blocks? It considers one block to be the single integer we've made, and the second block to be actually the array. So the single integer is 4 bytes. That leaves us with 28 minus 4, which is 24 bytes. And if you think about it, 4 times 6 is 24. So that's kind of where we're getting 28 bytes lost. 24 of that is coming from the array, and 4 is coming from the single integer, because they're both dynamically allocated. So let's go ahead and fix those problems. And by the way, if we were running it again, but this time let's say we did 10. We'd see that the array is indeed of size 10. And we can see this is basically 44 bytes in 2 blocks. Again, the 4 for the x value, which leaves us with 40, which that is easier to see that 4 times 10 is 40, right? So, yeah. Okay. So, we're like, oh, snap. Let's deallocate some stuff. So, we go ahead and deallocate the single variable. We don't deallocate the array because we forgot how to do that. So, we run it again. This time, let's do 100. We can see that we indeed have 100, and we can see exactly 400 bytes lost in 1 block. Again, that whole thing is just one delete that we forgot, basically. And so, how do we delete that? When you're deleting a dynamically allocated array, you do the weird syntax where you put the square brackets like that, and then you put the address that the array starts at, which is held in ARR. And voila, this should fix all our memory leaks. Let's put 999 this time, just for fun. We can see that it's a big array, but still 0 memory leaks, 0 errors from 0 context. That's good. Okay, so that is a 1-dimensional array. Let's make a 2-dimensional array now. That's more interesting. By the way, notice something here. Even though I'm using a pointer to create the array and everything, I can still access the elements of the array just like your previous arrays or like anything like vectors or whatever. You just put the ARR name or the variable name and then the square brackets. That's pretty nice, right? You don't need to do any weird syntax because it's pointers. So that's, I suppose that's one good thing. Now, let's make a 2D array. So here's the thing. You only have two news, per se. You have new, and like new, and then the variable type, like this. And then you also have this for a 1D array. But there's no such thing as a new with data type bracket for 2D array. You can't do that. So how are we going to make a 2D array that's dynamically allocated? Well, this is where arrays of pointers is going to come into play. Okay? So you can only dynamically allocate one-dimensional arrays at a time. Okay? So if you wanted to make a 2D array, which would kind of be represented as a table with rows and columns, you know, something like this, what you need to start thinking about this is kind of like an exploded view. Think of it as 4 rows with 3 items each, right? You need to make 4 new allocations, 1 per each row. Okay? So how do we do that? Well, what we can do is we can make an array of pointers, right? Because what can a pointer do? Well, if we're just trying to declare a one-dimensional array, we make a pointer variable, and then we make that pointer point to the first element of the array, right? That's how 1D pointers work. That's okay. We know how to do that. Well, guess what? What you need to do is you need to do that, but 4 times. So instead of doing them 4 times manually, just make an array of them, an array of pointers. So what I'm going to do is I'm going to dynamically allocate an array of pointers. So what will be the syntax for that? Well, we'll still need to know what the pointers point to, as in what the data type is. The data type is no longer an integer, right? It's no longer this, because that will be pointing to actual integers. But this, we're pointing to arrays. And for that, we need to make pointers. Like the array has to be made up of pointers themselves, not actual values. For that means that we need to change this from being just an integer array to being an array of pointers. And we do that by putting the asterisk right there. That tells me that this is no ordinary integer array. It is an pointer array. What kind of pointer? Integer pointer. Okay? So what this is going to do is this is going to make an array of size 4 with 4 pointers. Each of those pointers can then be made to point to each of the rows of the initial table up here. So we make that, we make that, we make that, and the same for the last one. And that solves basically how to make not just 2-dimensional, but you can use the same technique here to make any dimension that you want for arrays. But here's the thing. Where do you store this array? Well, all arrays need to be basically stored with a pointer, right? Because this is an address at the end of the day. So you're going to need another pointer to store the beginning of this array, right? So you actually need this array of pointers that we have here, but then that has to be stored somewhere, right? You need to set this line of code that I wrote up here equal, you know, and then put it in a pointer itself. So something like that. But this is not ordinary pointer. It's a pointer that points to other pointers. So it's a pointer to a pointer, which means that it's going to need 2 asterisks to actually get to the data itself, because it has to have 2 referencings, basically. One here, and then let's say it's going to go to here to go here. It requires 2 little asterisks per se, okay? Because if I do the little asterisk here, you would see that you pass 2 asterisks as you get there. If this was a 3D array, you would need 3 asterisks, right? Because you go pointer to pointer to pointer to actual data. So let us go ahead and create a 2D array in computer here. I'm going to go ahead and use this one for that. I don't know if I can actually, because I made it too big. Here, I have an idea. pasting the same thing in, but this time I'm shrinking it so that it can fit on that corner of the screen like such. Perfect. Okay. So, all right, going back to this, let's just let's make it in another program. We'll use Din2 for that. Okay, let me make sure the other one's still compiled. Yep, and Valorant, no memory leaks. Yeah, okay, cool. All right, so now we're using dynamic 2. Okay, so first we need to make let's make the outer one. Just make the outermost pointer. Okay, so that's the big array itself. So that one is not enough to do this, because again, this is gonna be a pointer that points to other pointers. So you gotta put a second asterisk for that. Okay, cool. That takes care of one of them. Now we need to allocate this. What are we storing in here? Well, we're storing an array of pointers. What kind of array of pointers? Integer pointers. So in this case, we'll hard code it to 4. But like I said, you could do the same thing I did before, where you can see in from the user. Okay, but I'm just going to do the exact same example to do for you here. Cool. Now we got to go through each of those 4 pointers that we have and allocate them. So for example, we could say something like array 0, which is going to be the first of the 4, equals to new int 3, because that's the number of columns that we have. Okay? Now I got to do this 4 times, like that. But that's a pain. Like, I don't want to have to type it that many times. So what can I do? I can just do a little for loop and basically make my life easier. So for that, I can say something like for int I equal to 0. I is less than 4 of them, because we need to make 4 of them. So basically it'll be the same number as up here. And then I plus plus. And then here I will switch this to I, because it's going to run first 0, then 1, then 2, and then finally 3. And there you go. If my calculations are correct, then this should be good to go. Okay? So let's, now that we created the array, let's go ahead and fill it out and then see out it. So we'll do that with another for loop. So, however, we actually need 2 for loops for this one. I mean, we could do 1 loop, but let's just do 2 because it's easier. So now that we've made the 2D array, you know, because it's a 2D array, we technically need 2 loops to be able to traverse it, right? Each loop is going to go per row and then per column, or if you go column first, I suppose you could do that too. So make sure you don't screw up the numbers 4 and 3 here. That was more of a personal comment, not to you guys, but to me. But yeah, all right. So then now that this is done, then we can go ahead and store it by saying ij equals, and I guess let's just do like a I plus j. Sure, why not? It's just a random number to store there. And then we will basically do the same thing, but I'm just gonna put it beneath it. No, because I want to show you that it's actually working. Otherwise, I could just do the C out there, but I'll do it in an entire new loop. For the sake of saving space, let's get rid of the semicolons because we really don't need them there. For this one, I'm going to leave them because what I'm going to do is I'm going to C out. So I want it to look pretty. I'm going to C out that spot and then put spaces in between. But for each line, I'm going to put in a line feed like that. So it'll look good like that. Trust. Yeah. Okay. Perfect. I do need the outer brackets for that for loop because of the C out statement. So yeah. Okay. So if we go ahead and run this program, we will see that it does generate a 2-dimensional array. So we just did exactly this. So to review this. What I did is first let's look at line 5. That's the kind of like the tricky line of this, the new line. This is an array of pointers because I can only make 1-dimensional arrays in C++. I'm doing this little quote-unquote hack to be able to have multi-dimensional arrays, which is instead of making arrays of actual data, I'm making arrays of pointers. Why? Because each of those pointers can point to their own arrays, as shown here. Okay? And that way, each of those arrays can represent a row in my data. Okay? See, this is the first row, this is the second row, third row, fourth row. So this would be with the actual numbers there, 0, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5. That's an interesting pattern. And that's basically what I wanted to do here. 0, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5. So that's basically the same thing that I am doing there, okay? I know you couldn't see the top one, but I just wanted to put it down. But yeah, so essentially, that's what it is. In fact, here, I can copy it so you can see it. Okay, so I have made this little 2D sort of table, you know, by making it a bunch of 1D things. Okay, I hope that that makes sense. You guys are very quiet today, so I'm just kind of going with this assumption that it makes sense. So yeah, the double asterisk is because it's a pointer to a pointer. Okay, and that's why you need a double asterisk on that first line. And then the single asterisk here is because this is an array of pointers, whereas this one down here is an array of integers. This is an array of integer pointers. This is an array of integers. Integer pointers, integers. Integer pointers, integers. Okay? So hopefully that makes sense. And so essentially I'm making 4 of these because I have 4 pointers and I'm filling them all up. Now, all that remains to do is to show you how to deallocate it, because I mean, this is big memory leak right here. I made a 2D array and I never deallocated, right? So, and by the way, pop quiz, I suppose. Are any of the variables in this program stored on the stack, or is everything on the heap? Now, have a dramatic pause for 3 seconds. 1, 2, 3, and give you the answer. The answer is there is something still stored on the stack here. The first one, this one right here. This is stored, this pointer is stored on the stack. This array, the pointer array, is stored on the heap, and so is the actual arrays with the data are stored on the heap. But there's still this one stored on the stack. Okay? So still understand that everything here is not dynamic. That first pointer is technically not dynamic. Okay? The pointer array is dynamic, but not the first pointer. We will see that's why we got tons of memory leaks here. And so we can see here that we have definitely lost this, indirectly lost. Oh, that's interesting. It says indirectly lost. So I wonder why it calls it indirectly lost versus definitely lost, but we can see what is happening here. This one out here, the one block here is probably the array of pointers, supposed to guess. And then this one here is each of the lines. Let's see, each of the lines would be 4, and this is 4 times 12, 3, 6, yeah. 4 times 12 is 48. That is correct. So that is coming from that. So these are definitely coming from the actual arrays of integers. And then this is coming from the single array of pointers. Now, why is the array of pointers so big when there's just 4 things? Because 4 divided by 32 is 8, right? Or 32 divided by 4. It turns out that probably addresses here are actually 8 bytes instead of 4 in this system here. Int I and j are from the loop are also on the stack. Yes, you are indeed correct about that. They are indeed in the stack as well because they're local variables here. So yes, they are. Good catch on that, by the way. If we wanted to be super hardcore, I suppose we could try to make them dynamic too. But I leave it to an exercise for you to do that on your own time. But yeah. So anyways, let's go ahead and fix these memory leaks. We still got 10 minutes, so let's fix them up. Okay. So when you're dealing with multi-dimensional arrays, you basically flip it upside down when it comes time to deallocate. So as you saw here, when you're building the array, you start out from like the outermost layer. You start out from here, then do this, and then do the individual arrays here, right? Okay. For deallocating, first we deallocate. Oh, sorry. First we're gonna deallocate this, and then this. And then this. And there's a very important reason as to why. And that is dangling pointers. Because if we say let's deallocate this right here first. If we do that, that would be the equivalent of me saying delete square brackets, because it's an array, of R. That is deallocating only the array of pointers, and we are not deallocating these guys. So technically speaking, background will say that I have definitely not lost that, but indirectly it'll say that I've lost that. So here, let's see how that happens. So oh no, it just pushed up the indirectly lost to the definitely lost area. That's funny. But yeah, so basically now I'm screwed here because technically speaking, I have no access to the internal part of the array. Now, could I do it? Yes. Would it work? Most likely it would, but it would be a dangling pointer. It would be me going into an apartment that I no longer own kind of thing. Okay? So let's leave it though, because I want to show you that even though it's bad, it'll most likely work. Let's go ahead and delete the internal arrays. How do we do that? Well, just take this for loop that you had up here and basically run it again, but instead of having the allocation, go ahead and do the delete. Like that. You still leave the RI part because you're deleting the 4 entries of your integer pointer array. Okay, so we're basically calling delete on this, on this, on this, and on this. Okay, that's what's happening in this line of code. However, this is bad because we've already deleted this, so technically we're accessing a dangling pointer here. So while this will most likely work and not even complain, it is bad and dangerous to do. See, I have fixed my memory leaks, but I do have some errors. I wonder if that's because of me trying to access something I shouldn't, or in the wrong order. Invalid read of size 8. Yeah, so this is probably, I'm getting these errors probably because I am accessing something after I've given it away. So yeah, bad thing, bad thing. So what do? Delete this pointer only until after you've deleted the inside. That's why you delete from the inside out, because then you don't run into an issue with dangling pointers. First delete these guys, and the way you delete them is you delete this, delete, delete, delete. Once you're done with this, now call delete on that and get rid of that as well. Okay? So if I do this, that should get rid of all the errors. So we can see here, no memory leaks, no errors. We still have a dangling pointer, technically speaking. So, okay, let's get rid of the dangling pointers. So this is something that I want to point out here. All I gotta do really at this point to stop any risk, you know, because technically speaking, I could like, here, I want to show you. Let me call the for loop again here. After I delete it. Segmentation fault. Oh, nice. So this time it's like, nah, you're not, you know, you shall not pass in there. But interesting. It actually crashed on me this time. It may have you know, it doesn't necessarily mean that that it would always crash, but in this scenario it did. But if I was to actually, like, just for the heck of it, before I call delete, let me access one of the, let me create a pointer, a temporary pointer here, and let me just copy one of the addresses. So like array 2 spot 1, okay? That's an address if I put the ampersand in front. So let's just get that into PTR, and then let's just go ahead and see out PTR. Because I want to show you that that memory still exists. There we go. Is that really spot 0? What would be spot 2? It gave me 0, but really, see, this is the delete here is doing sketchy things. It's actually, it seems like it's actually changing the values. But again, this is not standard, which means that it may or may not happen. If I run this on Sally, if you download this code running on your computer, you might get a different number here. But it didn't segfault, by the way, because what I'm doing here is PTR is actually holding an address of one of the locations in my array, which is this one. In fact, what is that address? Let's see that address. It's just going to be an address. If I was to go ahead and have and add into my for loop here another for loop that just prints out a bunch of addresses. Instead of actually printing out variables, it prints out addresses. By doing this, I would see that address 94 is right here. See? So I should get a 3 printed out. However, in this specific instance, it's saying that it's a 0 instead of a 3. So when I'm calling delete, this is actually doing something. That's the danger, see? Sometimes it would work, sometimes it would not. And so this happens to be a scenario where it doesn't work. This is a scenario where you walk into your house and somebody's already living there. Because into your old apartment, okay? So anyways, I showed you how to de-allocate the memory, but still, to be extra safe, to avoid things, you want to cut the links to it, just in case. And so what you do is you set this to null. Yeah, I don't think I need any asterisks there. Okay? That will prevent any problems, because here's the thing. You might be thinking, do I have to set to null each of the individual arrays? Each of the ones here. So like the entire array of pointers still has information in it. In fact, even though we saw that it's setting to 0 this, let's actually see what, well, first of all, let's see if it crashes. It's stored in an array like, for example, 1. I want to see if that address is still valid. Nope, it crashes it anyways. But technically speaking, oh, well, this one crashes obviously because I have the null here, so that's no surprise there. But let's move those like that. There we go. Okay, so it still contains the addresses of the variables. It's still containing them. In fact, actually, that it would be this line of code right here. Okay, array 1. This address is the same address as this because it happens to be where that pointer is stored. And so when you're getting rid of dangling pointers in multi-dimensional arrays, you don't need to manually set them all to 0, because as long as you cut, I would say, like I say, cut the head of the snake, you're okay. So basically, as long as you cut this, it doesn't matter that this internal array can still point to other spots. As long as you can't even get to the internal array by cutting that link off, then you're perfectly fine. So one single line of code will be okay to fix dangling pointers in general. Okay? So that concludes the lecture. So I hope that now you've got a basic idea of how to allocate multi-dimensional arrays and de-allocate them so that you can complete the assignment. Next time, we will be talking about shallow versus deep copy, which I believe the assignment also talks about. And then we will talk a little bit more about memory in general, probably for the rest of the day, and then maybe start virtuals next week. There's a lot of things to talk about when it comes to, oh yeah, that's right, I'm going to show you. I like showing you this. Most people don't show it, but I do. I don't think I was able to show it in the summer, but I'll show it definitely now. And that is how to do dynamic memory allocation in C, the C programming language, which you can do in this case here. Not because you necessarily good thing to use it, but because it's good to know. And that is actually also covered in the assignment. So if you see it there, that's cool. But if not, I'll show you on Thursday. So that'll be the goal for Thursday to do. All right. So hopefully you're all following along. If not, go ahead and let me know. I suppose, you know, very little interaction today. Hopefully the video is good. But until next time, I suppose, thank you for watching. Have a great week. And I'll see you guys on Wednesday.